In this video, we're going to be continuing our discussion on reactions with alkynes. So we've already seen that we can do hydrogenation, we can add HX, and we can add X2. In this video, we're going to see how we can do alkylation, which is a new reaction to us, addition of H2O or hydroxylation, and once again, as we saw with alkenes, we're going to see ozonolysis. So first we're going to look at alkylation. So we already saw that we can deprotonate terminal alkynes if we add a strong base like NaNH2 or NaH. And then when we react those two species together, we end up with the alkylidine salt. So that would be Na+, C-, and then their corresponding acid, so NH3 or H2, depending on what base you use. So this species here is both a strong base. Remember, it has a pKa of about 26, so that makes it a strong base. And it is also a good nucleophile. Both of these together make it primed for an SN2 or an E2 reaction. So what we see is we can do something like take a terminal alkyne. So say we take this alkyne here. We can add NaNH2. That will generate the alkylidine. And then we can add it to, say, a primary alkyl halide in DMSO. This is prep for an SN2 type reaction. And what we'll see is we will have SN2-like scenario. We'll have backside attack, kicking out Br. And we will end up with the alkylated product. So we've made this bond here. We've taken this species right here and reacted with the alkyne. So we've generated, I'll draw that again, we've generated the alkylated product. We can take this with a, say we're using the same species, we add it to NH2, we generate the alkylidine. We can also do this with methyl alkyl halides, so CH3Cl. This will similarly do an SN2 reaction, and we will end up with the 2-butyne. Now, this can only be done, this type of alkylation is only with methyl and primary alkyl halides, and we'll examine why we can't do that with secondary or tertiary alkyl halides. So say we wanted to do this reaction here. We're going to take the terminal alkyne, we're going to add NaH this time, so we lose H2. We generate the terminal alkylidine. And say we add it to this alkyl bromide here. If we weren't careful, we would expect, backside attack right here, kick out the alkyl bromide, and we'd end up with this species here. This is not the species that occurs. If we remember, this species is a strong base. It's a good nucleophile and a strong base. If we have a secondary or a tertiary alkyl halide, instead of doing the SN2 reaction, we're actually going to do the E2 reaction. So instead of generating the alkyl bromide, we'll simply do an elimination reaction and generate the alkene and regenerate the terminal alkyne product. So with secondary alkyl halides, we generate the E2 product. With primary and methyl alkyl halides, we are going to generate the SN2 product fully. One of the benefits of this is we can use this to extend chains. So say we wanted to take this alkyne and add NaNH2, and we get the alkylidine. Then we say we add it to the same alkyl bromide we saw before. So we end up with this product here. So this is 2, 1, 2, 3, 4, 5. This is 2-pentine. And then we could do something like H2 on platinum and reduce it to pentane, 1, 2, 3, 4, 5. So we've extended the chain from a 3-carbon length to a 5-carbon length. So this is a good way to extend carbon chains if this is something we're looking to do, build them. Or you can imagine we could then take this to, say we wanted to do this Na and NH3. We could take this to the transalkene 1, 2, 3, 4, 5. We could take this to the 2-pentene if we wanted to. So a good way to extend chains and do to make carbon-carbon bonds. So now we're going to look at hydroxylation in 3 different cases. We've seen 3 different ways we can add HOH across a double bond. Those are acid catalyzed hydration, hydroboration, and oxymercuration. And it turns out that we can do the same thing with alkynes. So let's look at acid catalyzed hydration first. So if we took a alkene, we added H3O plus, we would add the Markovnikov OH and H. We'd end up with the secondary alcohol, and this is going to be Markovnikov addition. It turns out we can do the same thing with an alkyne, add H3O plus, and we will add Markovnikov, the OH, again reducing it to a double bond, and we will end up with the internal OH. This species here, this functionality that we see here with an alkene and an alcohol, we call this an enol, ene for alkene, ol for alcohol, and it turns out that enols are unstable. Enols are an unstable form of what we call a tautomer. So a tautomer, spelled Tautomer, a tautomer they are constitutional isomers that differ by a proton transfer. So what we can do is we can move protons around in this enol form to get a more stable form of this species. So it turns out that enols and carbonyls are going to be tautomers of each other, and I'll show you the tautomerization pathway for this. Say we have this enol here. Okay, say we have this enol here. One thing we can do is we can push, here let me draw exogenous water. So this is usually in water or alcohol. What we can do is we can push these electrons down. We can have this grab a proton and push out OH. Actually, this is more likely OH2. This is usually an acid. What we'll be left with is a double bond OH. We've gained an H here. And we have R prime. This is an OH plus, and this can be once again plucked off by OH2, the water that we just generated in the previous step. And what we're left with is we see that the enol is a tautomer with a carbonyl. So it turns out that enols, I'll draw an enol. Enols are tautomers with carbonyls. And if this R is an H, it's going to be an aldehyde. If this R is truly an alkyl group, then it will be a ketone. So depending on whether this R group is an aldehyde, is a H or an alkyl group, this will be either a ketone or an aldehyde. So when we look at this species, when we do the acid catalyzed hydration of propyne, we're going to have this enol intermediate, but the final product we'll actually get is acetone. We're going to have the tautomerization to acetone. It's not going to stop at the enol intermediate. And we can see that with terminal alkynes, we will end up with the aldehyde in certain situations. So we saw that with acid catalyzed hydration, we're going to end up with the Markovnikov addition of OH. That's our enol form, and then we'll tautomerize to the ketone. Recall that we also have Markovnikov addition if we do oxymercuration. So that's Hg. In this case, it's HgSO4, which is a little bit more stable to alkynes than mercury acetate and H2O. Oxymercuration reduction, so we'll have NaBH4 and NaOH. This will also end up with the Markovnikov addition of OH, and we will tautomerize again to the ketone. Furthermore, if we do the hydroboration, so that's R2BH, followed by H2O2 and NaOH, remember this will add anti-Markovnikov, so that's going to add the terminal OH. And this is a case where that R group is an H, so we will end up with the aldehyde in this case. So we will end up with this species here. So we've changed the location where we've added the carbonyl, whether we've added a Markovnikov or we've added an anti-Markovnikov. So depending on what we're doing, we'll generate the intermediate enol species, which will then tautomerize to either the ketone or the aldehyde. depending on whether we're doing a Markovnikov or an anti-Markovnikov addition of the alcohol. The final reaction I want to talk about is ozonolysis. So as we saw with an alkene, ozonolysis is O3 and then Me2S or H2O. That's going to generate two carbonyls. So we end up with these two carbonyls here. So it basically cleaves this double bond right down the center and oxidizes it to the dicarbonyl. Ozonolysis on an alkyne will do a similar reaction. So Me2S or H2O. It's similarly going to cleave that triple bond right down the center, except now instead of being left, we had extra groups here. We had H and we had HH. In this case, we only have one group, so we're going to fill that extra group in with a OH. So ozonolysis on a alkyne generates carboxylic acids. Ozonolysis on an alkene generates carbonyls. If you were to do this with a terminal alkyne, so you do O3 and say water, we generate one carboxylic acid that corresponds to these carbons here. Then we have a terminal alkyne, which would represent the this carboxylic acid here. So ozonolysis will result in carboxylic acids when done on alkynes instead of the carbonyls that are generated when you do this with alkenes.